Good day everybody. We are expected to integrate integral negative infinity to infinity e raised to the power of negative x squared times dx, and we have to show the value to be equal to root of pi. This is called the famous Gaussian integral. Now there are many ways to solve this. I would be employing Jacobian's technique to solve this. So foremost, what I wish to do is I would like to consider let I be equal to integral negative infinity to infinity e raised to the power of negative x squared dx. Now this is an even function, so I can rewrite this as 2 times integral 0 to infinity e raised to the power of negative x squared times dx. Now let me rewrite this. So I have taken I to be equal to 2 times integral 0 to infinity e raised to the power of negative x squared dx. Now this can be also be rewritten as 2 times integral 0 to infinity e raised to the power of negative y squared times dy. Here the variable is x, here the variable is y. So there aren't going to be any change or alteration in the outcome. So I can very well take this and then equate it to y. That is acceptable. Now what I wish to do is I would like to perform the following manipulation. So consider I into I. Now this is nothing but for the first I am going to write 2 times integral 0 to infinity e raised to the power of negative x squared dx multiplied with, for the second I, 2 times integral 0 to infinity e raised to the power of negative y squared dy. Now I am clubbing both the things together. This is equal to 2 squared integral 0 to infinity e raised to the power of negative x squared times e raised to the power of negative y squared times dx dy. Now I'm going to use the Jacobian's technique. So a brief view of the Jacobian technique. What exactly is the Jacobian technique you need to know. Now suppose you are given an integral, say I is equal to double integral f of x comma y times dx dy. This is the region. Then you can very well assign x to be equal to, x is equal to x of r comma some theta, and y to be equal to y of r comma theta, such that now dx dy is equal to modulus of det, it's called determinant of j. I will show you what exactly this means, times dr d theta, right? So this is the formula. With this formula you can simply annihilate the double integral, because sometimes, or I would say most times, integrating that to a function with double integrals under the Cartesian banner, it's cumbersome. But with polar form r and theta, you can, and with Jacobian technique, you can simply annihilate the integral. That's exactly what I'm going to do here. So with this formula, this is going to be equal to, and let me just give you the Jacobian j. J is nothing but dou of x comma y over dou of r comma theta. Now this has got a formula which you can actually place this here. So first case, dou x over dou r, you need to find this, and followed by dou x over dou theta, and then dou y over dou r, and then dou y over dou theta. You need to get the determinant. That's it. It's simple, right? So once you get the determinant, and then you multiply this with dr times d theta. So let us do this. So first I need to define the x component. So I need to take x is equal to, I'm going to take x is equal to r cos theta and y is equal to r sin theta. Now you got this integral, right? So you can very well write this as 2 squared is 4 double integral 0 to infinity e raised to the power of negative of x squared positive y squared times dx dy. This is what we are going to be targeting. So using Jacobian technique, you are going to convert everything into polar form. Foremost, let us find what is x squared positive y squared, because we need to substitute that. So this is nothing but x is r squared cos squared theta, y is r squared sin squared theta. This is nothing but r squared of cos squared theta plus sin squared theta, which is equal to r squared of 1, which is equal to r squared. So this is my x squared positive y squared. So this is done. Now we don't have much space here. I can try to squeeze it. Let me see. So this is equal to modulus of dou x over dou r. Now x is equal to r cos theta. Dou x over dou r will give me cos theta. Dou x over dou theta, that's going to be negative r times sin theta, because we're differentiating with reference to theta. Sin theta. Dou y over dou r, so this is going to be sin theta, and dou y over dou theta, that's going to be r into cos theta. Now you multiply this cos theta, r cos theta into cos theta, that's going to be r times cos square theta. When you go this side, you need to carry a negative sign, so that will make this quantity positive, r times sin square theta. So this is going to be r of cos square theta positive sin square theta, which is going to give me r. So this determinant is nothing but r. So what I need to do is, when I am having dx over dy, I need to replace it with r times dr d theta. Simple, isn't it? So let me take this as some 3. I need to go to the next page. So therefore I can rewrite 3. So what is 3? This is equal to 4 times double integral 0 to infinity e raised to the power of negative x squared positive y squared dx dy is equal to 4 times. I'm not going to touch anything with the limits as of now. E raised to the power of x squared positive y squared is r squared. Dx dy is r times dr times d theta. Now this is the angular variation. This is rewritten as, this will be setting from 0 to infinity, but theta, this is going to be moving from 0 to pi over 2. That would be the variation we will have for this integral. So now we need to integrate this value. So what I'm going to do is, I'm going to integrate this quantity first. So if I were to take r squared is equal to some u, 2 times r dr is equal to du. I got only r dr, so this is going to be r dr is equal to du divided by 2. So 4 times integral 0 to pi over 2, that's placed there. Now the limits are going to be as it is, right? There's not going to be any change, but the values for this is going to be e raised to the power of, I will place the integral sign, negative r squared, that's going to be negative u, r into dr is going to be du of 2 there, 2 I'm placing it there. So now we need to place the d theta there. Now the limits is going to be 0 to infinity, there's not going to be any change, because when you have r is equal to 0, u is 0, r is infinity, u is also infinity, so that will not have any impact at all. So it's going to be 2 times integral 0 to pi over 2, and integration of e raised to the power of negative sign there. So integral of e power negative u is going to be negative of e raised to the power of negative u, right? So there will be a presence of a negative sign here, so we need to cater to that sign also. So this is going to be 2 times limits are 0 to pi over 2 d theta. So this is equal to 2 times of theta 0 to pi over 2, which is equal to 2 times of pi over 2, which is equal to pi. So this is what we've got. So what is this exactly? This is nothing but, if you were to see the original system, we had actually I into I, right, if you remember. So this is nothing but I squared, and on the right hand side you got pi. We need only I, so this means I is equal to root of pi units, and this is the famous Gaussian integral. This implies integral negative infinity to infinity e raised to the power of negative x squared times dx is equal to root of pi, and this we have achieved beautifully. So that is the solution for this question using Jacobian technique. Thank you everybody, enjoy your night.